In this video, we will begin our look at electrophilic aromatic substitution by first considering the reactions of both alkenes and benzene with electrophiles. By now, we've spent a lot of time talking about how nucleophiles react with electrophiles. And in many cases, we have a nucleophile that has a lone pair of electrons reacting with an electrophile, which may have a full positive charge, or at least it has positive character. And we think about our nucleophile sharing electrons with the electrophile. But we've also seen some examples where the nucleophile does not necessarily have a lone pair. Instead, it just is something that is electron rich. For example, we could have an alkene act as the nucleophile and share its electrons with the electrophilic species. So for example, if our alkene shares its electrons with the electrophile, pushing away the Y group, that can give us this intermediate where, let's say, the carbon on the left becomes connected to the electrophile. That leaves the carbon on the right with a positive formal charge. And then Y was the leaving group. Now, in a second step, they change roles so that now this is the nucleophile and this is the electrophile. So Y can share its electrons with this carbon, leading to something like this. Now, I'm not trying to show anything about stereochemistry or the relative positioning. What I want to call your attention to is that the two carbons that used to be the alkene carbons, one of them is connected to the electrophilic part of what was originally EY, and the adjacent carbon is connected to the Y group, whatever that represents. So in the case of alkenes, we have electrophilic addition, where these two parts are added across the double bond. What happens if we're talking about benzene? Benzene and other aromatic compounds do not necessarily react the same way as typical alkenes, but they are electron rich, and so it's possible that an aromatic compound can share its electrons with an electrophilic species. So that would look like this, and in this case we're going to push away that Y group, and that gives us this intermediate. So let's say that this carbon is the one that becomes connected to the electrophilic species. Remember, we still have only one hydrogen here. We no longer have the double bond. So now this carbon has a positive formal charge, and these two double bonds are still here. And we have our Y species. Now there's two different things that could happen. If this reaction was analogous to what we just saw with alkenes, then this would share its electrons with this carbon, leading to this type of species. Once again, it's electrophilic addition, where the E group and the Y group both have added across one of the double bonds of the benzene. But notice this is no longer benzene. Okay, this is no longer an aromatic compound. Aromaticity was destroyed because of the electrophilic addition. Alternatively, if this Y group, instead of acting as a nucleophile, if it acts as a base, it could grab off this proton, allowing these electrons to fold in here, and that is going to recreate the double bond. So in that case, we get our double bond back. This carbon is still connected to a hydrogen, and this carbon is now connected to the E group. And in this case, what we have is substitution. So this hydrogen has been replaced by the electrophilic portion of whatever this EY represents. So this is electrophilic aromatic substitution. electrophilic aromatic substitution. So while alkenes can undergo electrophilic addition, which means that the alkene reacts with an electrophile and the net result is addition of the two portions across the double bond. Benzene or other aromatic compounds can react with an electrophile with a temporary disruption of aromaticity, but then aromaticity is restored. The net result is a substitution. Let's consider some of the electrophiles that we have seen alkenes react with. Some of the most straightforward ones, we had HX, we have X2, or we have H3O+. So let's think about this as an energy diagram where our energy is increasing in this direction, and then here we have our reaction progress. So let's start out with our alkene, and let's say this represents our starting energy of the alkene. Then this would represent the intermediate, and then maybe this represents the energy of the product. Now, I'm really not trying to say anything about the relative energy of the starting material compared to the product. What's important is the relative energy of the starting material to the intermediate, the carbocation. This is important because the relative energy of this intermediate is related to the relative energy of the transition state. And keep in mind that the transition state, or the relationship between the starting material and the transition state, this determines the activation energy, which determines how quickly a reaction can proceed. Now, right next to this energy diagram, here is another energy diagram, and we're still talking about the energy increasing in this direction, but now we are talking about benzene. And let's just line this up so that our starting point is the same. So I'm not saying that the energy of benzene is the exact same as the energy of this alkene. We're just setting these up at the same starting point so that we can more easily compare the energies of the transition state and intermediate. Now we know that aromatic compounds have a special stability, so that means that our carbocation, not only is it higher energy because it's a carbocation, but it's also much higher energy because it is no longer aromatic. So if this was the relative energy then of the carbocation intermediate corresponding to the alkene, then in the case of benzene, well, maybe that carbocation intermediate is going to be way up here. Okay, much, much higher energy. And that means that the transition state leading to it is also going to be very high energy. So in this case, we are now looking at an activation energy that is much, much larger for the reaction of benzene with an electrophile compared to the reaction of an alkene with an electrophile. So what this really means is that these electrophiles that were reactive with an alkene, they're not going to be good enough to react with benzene. And so reaction with benzene requires even stronger electrophiles for any reaction to be able to occur. Furthermore, let's consider the two possibilities for reaction once we have formed this intermediate. So if our Y group was to act as a nucleophile and add to this position, then we would get our product that would look like this. And That hydrogen's still there, and now our Y group is connected. And let's say this represents the energy of this product, and then we're going to have some activation energy that leads to that product. But the alternative was that the Y group would act as a base and abstract this proton, allowing these electrons to reform the double bond and restore aromaticity. That would lead to this product, and this is going to be much, much lower energy. I'm not trying to say anything about the relative energy of these two, but they're going to be at least similar because in both cases we're talking about either benzene or a substituted benzene. And then perhaps this represents the reaction progress. So here is the activation energy leading to a much, much, much more stable product. So once again, we can compare the reaction of an electrophile with an alkene compared to with a benzene. In both cases, it leads to a carbocation intermediate. In the case of an alkene, this is high energy, and the transition state leading to it is high. In the case of benzene, the carbocation intermediate is extremely high energy because it's a carbocation and it has given up aromaticity. Therefore, the transition state leading to it is also very high energy. After this intermediate has formed, then this molecule can follow two different pathways. This pathway is unfavorable because it leads to a still high energy product, whereas the blue pathway is much more favorable because aromaticity is restored. So this is why benzene will undergo electrophilic aromatic substitution rather than electrophilic addition. So let's take a look at a few examples of electrophiles that will react with benzene. If we treat benzene with a mixture of nitric acid and sulfuric acid, this will carry out a nitration in which a hydrogen on benzene is replaced with a nitro group. So these conditions lead to the formation of this as the electrophile, and then this is the final product. A second example, if we treat benzene with sulfuric acid or what's called fuming sulfuric acid, a mixture of sulfur trioxide and sulfuric acid, that's going to give us SO3. This is the actual electrophile, and that leads to the formation of this sulfonate. And so this is called sulfonation. If benzene is treated with a halogen in the presence of iron or in the presence of iron trihalide, then this generates an electrophile that looks like this, and it leads to the substitution of a hydrogen by a halogen. And so this is called halogenation. If benzene is treated with an alkyl halide in the presence of aluminum trihalide, that will generate an electrophilic species that looks like this type of complex, or it could just be a carbocation, and that leads to the substitution of an alkyl group for the hydrogen. This is called an alkylation. And related to that, if we treat benzene with an acid chloride or an acyl chloride, this is an acyl group, and that's typically combined with aluminum trichloride, and that generates an electrophile that looks like this, and that leads to the substitution of an acyl group for the hydrogen, and this is called an acylation. So this provides an overview of some of the electrophilic aromatic substitution reactions that can happen where using these sets of conditions generates
these electrophiles leading to these substitution products.